So previously, what we did for chapter 3 is to test an hypothesis like this, right? So it says, what is the population average income in Korea? So the suggestion by the null says it is some number, like $30,000, something like that. And the alternative says, no, it's bigger, okay? And then you have to make a decision between two. So this is what we did. Today, we are going to show you something like that. The only difference is the alternative. And from the statistics, you know that this is one-sided test. Sided. And this is two-sided. Okay? So we did it before. This is something we want to do today. It's almost the same, so it'll be a review. Okay? Now a few things to remember. First one. The sample mean has a distribution, right? The mean of the sample mean is equal to the population mean, right? But the variance of the sample mean is much smaller than the variance of the population. Do you remember this? So this is something we did in the exam too. If the sample size is big enough, then we can say that distribution of the sample mean follows a normal distribution with the center at the population mean and the variance equal to population variance divided by the sample size. So as n grows, the y bar, the sample mean, becomes more and more concentrated around the true value, population, okay? Unknown truths. I have a few things to say about this. Now this value is actually the variance of the sample mean, right? And as you can see, the variance disappears as n grows, and this is one condition to claim that y bar is consistent, right? The second condition is y bar is unbiased. Now, the standard deviation is a square root of this. So if you take the square root, it's going to be the standard deviation. Now, what if the population variance is unknown? What if then we cannot use this distribution anymore because this part is unknown, but we can estimate the population variance. We can use the sample variance to estimate this population variance, right? So when the sigma squared is unknown, at least we can estimate the variance of y bar by using s squared in place of sigma squared. So kind of looks weird, but let me write it in this way. Now variance of y bar is unknown, but we can still calculate something close. Because this is something we calculate using the sample information, I put hat. So does it make sense? So this is our estimate for the variance of y bar. That's what it means. It kind of looks ugly. So let me draw it again. So that's our estimate for the variance. Now what is the estimate of the standard deviation? So that's when you use s in place of sigma, right? So what is s divided by square root of n? So one way is to write down standard deviation of y bar, but our estimate. So this is one way to write it down. Or because we are going to use it so frequently, we just provide a new name, standard error. Okay, so that's the standard error of y bar. So let me just write it down. SME is standard error. So that's given by this guy. So there are two possibilities. If sigma squared, the population variance, is known, then you can use this distribution, right? If sigma squared is known. If it is not known, then at least we can estimate this part of the normal distribution, and hopefully, as the sample size grows, this approximation becomes more and more accurate. So I like to say two things about this. So this is when sigma squared is known. This is when sigma squared is unknown. Usually sigma squared is unknown, so we are going to use the second, right? Mostly. So I have two comments about this. Now, in either case, this part is fixed because we know sigma squared, right? So this is a value. What is not fixed, what is unknown is this part. This part is fixed because we can calculate s squared using your sample. But this is unknown. So think about the normal distribution. It has mean and variance. Variance is known or fixed. In any case, what is not fixed is the mean. So the role of the hypothesis is to fix the mean too. Okay? If null is true, everything about this guy is known. Okay, so that's how we use the information in the hypothesis. Does it make sense? Now, this part is known because it's assumed to be known, or we can calculate. This part is known because we assume that the null is true. Now, everything is fixed. You can calculate probability using this normal distribution. Okay? It's all review. Okay? My second comment is this. So that's the role of the hypothesis. You can standardize it, right? So in the first case, when sigma squared is known, we define a G statistics. Then this follows normal distribution with 0 and 1. When sigma squared is unknown, we define a T statistics. This is how you standardize your normal distribution. Follows standard normal distribution 2, right? So that's where this notation comes from, G and T. Now let's use them and let's figure out how to test these hypotheses. So what is right? What is correct given our information? Like before, the first method is the rejection region method. We simply call it RR, the rejection region. So what is the rejection region? Now, before you draw any sample, kind of think about the whole situation. So we know that y bar follows a normal distribution. So let me focus on the second case, okay? So if the null is true, the distribution of y bar is centered at the population distribution under the null. And you know that one standard deviation is given by this. The sample size is big enough, it is typically small. Okay? Now you draw your sample, calculate your y bar. If y bar is close to mu null, then there is some evidence that the null is true. But if y bar is far from the center, then you may think that this is unlikely. So maybe the null is false. The alternative is true. Now, under this alternative hypothesis, y bar can be far from the center because it is too big or because it's too small. So there are two rejection regions. Okay? Unlikely area under the null. So we want to calculate these two rejection regions. So the rejection region is, and y bar is too big, bigger than some cutoff, upper cutoff, this is YU, or y bar is too small, smaller than a very small value. So how to make a test? So we think about the significance level. And that's the probability of reject the null when null is true. If the null is true, then we know the distribution of y bar, right? So that's the distribution of y bar under the null. When you reject the null, when your sample mean is in the rejection region. So it's either it's too big or too small if the null is true. So I'm not going to write the whole thing, it's too long, okay? So given H null means if the null is true. So there's no overlap, so you can separate them. Sum of these two probabilities must be equal to alpha, right? So isn't it reasonable to give half of alpha over here and half over here? Do you think that's reasonable? So we assign the same probability on the left-hand side and right-hand side. So let's think about how to calculate this upper bound. Okay? The rejection region to the right. So how to do that? So let's remember that this is the hypothesis, okay? Now suppose that alpha is 0.05, 5%, half of it is 0.025. So let's think about this probability. Half of the alpha must be equal to now we standardize. So I just used this information, so let me just drop the condition, okay? So this probability must be 0.025. When that's the case, it is when this value, oh, by the way, let me just write one more step. Do you remember that this is the t value? Now, when this probability is equal to 2.5%, that's when this value is 1.97 or 96. Really doesn't matter. So we just find out the rejection region to the right. Okay? So that's how you determine a rejection region. So mu null center is given by the null hypothesis. Null status is 30,000 something, okay? 1.97 just number. This is the sample standard deviation, something you can calculate. Square root of sample size. So everything here is calculable. So that's how you determine the right-hand side. Now, I just used 2.5% probability here. I'm going to use the remaining 2.5% and find out the lower bound too. So you can do it. Try that later. So that's the lower bound. So we just find out the rejection region. So what's our rejection region? It is so again, this is the situation. So you make these calculations before you draw any sample. So this is before you start any investigation. Okay? Now you make your effort, you do the research, collect sample, and then you get your sample and get the sample mean. If the sample mean is inside the rejection region, we reject the null. If it is outside, we fail to reject the null. Okay? So reject. So that's how you make a decision. So you determine the rejection region first, and then you draw your sample. If your sample mean is inside of the region, you reject the null hypothesis. Now, there's really nothing new here. Another way to say this is this. So when do you reject? When your sample mean y bar is bigger than this. What does it mean? If I just write it again, is when the standardized value is bigger than 1.97. And we know that this is the t value, right? So that's the right-hand side. Again, when do you reject? If your t value is, so 4, then you reject. So it's very familiar, right? So you calculate the t value, which is a standardized sample mean. And then if it is bigger than or smaller than 2, approximately, you reject the null. Right? 2 or minus 2. So the p-value method is actually the rejection region method. Do you have any questions so far? It's very hot, right? Can you open the door? That door? Now we have 1.5 months to go. It'll be very hot in this room. So that's our first method. The second method is the p-value method. Now it's kind of different, right? The first method, you make all the calculations before you draw your sample, and then you only make decisions after you draw your sample, right? So that's how you calculate. Now this one is kind of different. You draw your sample first, and then you calculate something, okay? And then you ask yourself, what if I redraw my sample independently? What if I do this investigation again? Am I going to get the evidence as strong as the evidence I have right now? So what is the chance that I have an evidence that goes against a null that's as strong as the current evidence, the evidence I have? So it's a kind of different story, right? So the p-value is, what is the chance? So suppose that small y bar is the sample mean from your sample. Okay? So this is the evidence you have against the suspect. And you ask, if I do it again, if everything just happens again, and I do this sample collection, what is the chance that this imaginary sample provides the evidence which is as strong as my current evidence, right? What if my new sample mean is as strong or as extreme as my current one, assuming that the null is true? Now, one problem we had before is this is a continuous random variable. That's equal to one value is just 0, meaningless, right? So we just add as extreme, as strong as mine, or even more extreme, right? It's kind of compromise we have to make. Now there's one more problem. Now the thing is that this is before you draw your second, you never draw the second sample, right? But this is something that you have to think about before you draw your second sample. But we have this two-sided hypothesis. So when you say as extreme as my current one, it can be as extreme because it's too big. Or it can be as extreme because it is too small. But too small means equally extreme, right? Just to be consistent in logic, we have to think about the probability over here, but the probability over there too. Now everything is symmetric. So if you only care about the probability to the right-hand side, the probability on the left-hand side will be the same, right? So that's why we multiply 2. And then we can calculate this probability. If the null is true, we know the distribution. Now, small y bar is the sample mean of your sample. Mu 0 is given by the null hypothesis. Sample standard deviation, you can calculate square root of n, obvious. So you can calculate everything here. And p follows a standard normal distribution, right? So you can use the table, you multiply 2, so you can calculate p value. And you know that if the p value is smaller than alpha, you reject them. So as I said, the idea is you not reject the null when the p-value is very small. But how small is small enough? That's given by the significance level. And the p-value is very small. It means that if you repeat, it's very unlikely that you have another y bar which is as extreme as your current y bar. It's not going to happen. What's the problem? Maybe your assumption is wrong. Okay? Maybe your assumption was very unreasonable, so we have to doubt it. Okay, so that's the story. But again, I think it takes about 1 month or 2 months to study these things in statistics. So it's kind of unrealistic that we can review everything. So you have to add a lot of details to this basic structure. Okay? So how do you do that? So I was thinking about it, and one kind of efficient way is to solve some homework exercises. So that's why you have this new assignment. If you go to the class website, can you go to the class website? Now, do you find assignment 6? So that's what's new, okay? So I list 3 exercises from the textbook. So maybe that's how you make yourself familiar with all those things. So this is the new assignment due by Wednesday. So that's right before you have this long break. You just work out your homework, submit it, and then you can enjoy your break. Okay? So I think you can solve everything in chapter 3 right now. And these two questions from chapter 5 is something we are going to do today. Okay? So after today, you should be ready to do everything. So assignment 6 will be very important too for the coming quiz. So I believe we'll work hard to do this thing. Okay? Just try them. So how about Tuesday then? So let's make it by Tuesday. Okay? I think that's fair. So let's do it this way. So it's optional. If you want, you can submit it on Tuesday. Okay? But some of you have to, because you cannot be here. Otherwise, it's by Wednesday. By the way, because I was talking about this coming quiz, we are going to have the 3rd quiz once I finish chapter 5. Okay? It covers 3 and 5. Chapter 3 and chapter 5. So that's after break. So you're gonna enjoy your break first. Okay, so that's the end of chapter 3. And we start chapter 5. So the same idea, there are 2 hypotheses, competing hypotheses, and we like to choose which one is correct. The only difference is we like to choose in the regression problem. So the hypothesis typically looks like that. Now what does it mean? What does the null says? Now suppose that the slope is 0. What does it mean? What kind of line do you have? The line is flat, right? Suppose that x is the class size, y is the test score. What does it mean when you have a flat line? So if you compare two schools with class size of 15 and 30, does it make any difference? No, right? So then if the null is true, the class size doesn't matter, at least for the test score, right? Now what does he say? It matters in some way. So this is one possibility. Now, this is more specific, right? So now it says class size doesn't matter. But Turnip says what? It matters in some way, right? But it provides a direction. If you increase your class size, the test score must go down. That's the alternative. Because in some sense, you provide more information. By making your problem like this, you kind of assume that the other way is just impossible. So that's why I just excluded. Okay? So this is one possibility. Another possibility is something like so now it says it matters if you no, it's got to be minus. If you increase your class size by 1, test score will go down by 1.2 points, right? So it matters in some way. So here, the null hypothesis is kind of very specific. Okay, so out of all these possibilities, we are going to study this one because that's what we ask in most cases, but you can extend it and ask how to make a decision between these two, or you can ask how to make a decision between these two. Okay? Do you have this reading guide? Do you have this notes? So I suggest 4 steps. So let's follow these 4 steps to make a decision. So step 1 is to calculate the standard error. Now what is the standard error? The standard error of y bar is this, right? But our question is about regression, conditional mean, not the marginal mean. So we ask, what is the standard error of beta 1 hat? So that's going to be the question. So what is it? Now the standard error is an estimate of the standard deviation of this random variable. Right? So to figure out the standard error, you have to think of the standard deviation first, or the variance of the beta 1 hat. So let's think about variance of beta 1 hat. So this is formula from the textbook. So how we can calculate this? It looks complicated, but it is really not. Everything comes from the formula you already know very well. Do you remember this formula? Now you just plug out what is your yi. Your yi is something like that. What is your y bar? Then you can calculate your y bar, and you plug these things over here in this expression, and then if you work it out, and you calculate the values, and that's it. And you can get this guy. Okay. Again, in old days, the whole point of having a class is actually to calculate this. But we're not going to do it. Instead, we can use simulation just to convince ourselves that this formula makes sense. So let's just try to understand what this is all about. Now the denominator is kind of simple, the variance of xi squared. So can you imagine that you just calculate the sample variance of your independent variable? You type variance of x, okay? And then you square it. Although it's a population variance. Now numerator is kind of tricky. It's a variance of the whole thing. So you have your xi, and you subtract the mean of the xi. You center your xi, so that's this side. You have the error ui, and you center it. You subtract the mean. But the thing is, the mean of ui must be equal to 0, right? By assumption. So you can conveniently ignore this term. So in a sense, you multiply xi and ui, and then you calculate the values. Okay? So you make a new random variable, and you wonder what is the variance of the new random variable. And then you compare it against the variance of xi squared. Okay? So that's the variance of beta 1 hat. Again, we are not going to prove it, but if time allows, we'll use some simulation and make an argument that this makes a lot of sense. So that's the variance of beta 1 hat. Standard deviation is the square root of it, right? Now, standard deviation depends on the variance of xi in the population. And variance of xi times ui in the population. They are unknown. So the standard error is an estimate of these things. And this is how. So the idea is when the variance is unknown, we use a sample variance, right? So basically, we just use that idea. Variance of x is unknown, so we use a sample variance of x. What about this? The mean of x is unknown, so we use sample mean, the population mean, and xi minus x bar, and we square it because we have to calculate the variance. UI is unknown, but the residual is known. UI hat is known. So we use UI hat in the place of UI. So everything kind of makes sense, right? But the tricky thing is why we want to use n for the denominator. and n minus 2 for the numerator. So why that's the case? So I have two comments. If the n is big enough, it really doesn't matter. If n is 5,000, n minus 1 and n minus 2 are kind of about the same. Okay? So we care less. It matters when n is very small. So people, at least the textbook, make this choice because they believe that it somehow provides a good how can I say, good outcome, good result. In some cases, okay? It cannot be the best solution for every cases, but at least it provides a good outcome for many cases. So that's why they choose n and n minus 2, these factors. Okay? So by the way, anyway, that's the first step. Calculate the standard error. So this is how. So when you have your x and y, you can run the regression, you find out the residual, you use this formula, then you can calculate the standard error of the regression coefficient. Now, do you have to do it? Or do you have to use this formula exactly? The answer is definitely not. Okay? You don't have to know this. We are going to use the outcome from R. This is not something you have to memorize. But just, remember that there is a formula out there in the textbook, and it tells you about the standard error. Okay? Now remember that under the null, beta 1 is equal to 0. Okay? The flat line, and we have a two-sided alternative. That's what we do now. Now step 2, t-value. So what is the t-value? T-value is by definition beta 1 from my sample minus beta 1 under the null hypothesis. It's like mu under the null, right? In chapter 3. So what is the beta 1 under the null? What does the null says? 0. And it divided by the standard error of beta 1 hat, right? So compare it against t-value we had before. So we essentially have the same thing. The sample mean minus mean under the null divided by the standard error of the sample mean, right? So we have beta 1 hat minus beta 1 under the null divided by the standard error. So there's no difference. So where is the square root of n here? Used to have the square root of n. We still have it here, just hidden in the formula, okay? The square root of n is already taken care of. So that's step 2. Actually, you can make a decision already. You reject the null if t is too big or t is too small. It's the same rule. So this t-value method is actually the method 1, the rejection region method. What about p-value? If you want to go further, the step 3 is p-value. So how to calculate the p-value? P-value is the probability of beta 1 hat of your imaginary sample, of your second sample, bigger than beta 1 hat in your current sample, right? Now, I'm in trouble. I cannot use the lowercase letter for beta 1 hat. So I have some kind of issue here. So the textbook says beta 1 hat ACT. What does it mean? So that's the actual value of beta 1 hat. It's like lowercase y bar. Okay? So that's the p-value. So this is beta 1 hat. You have your sample. So if you run a regression using R, this is something you will get from the outcome. Now you start to ask, what if I collect another sample and run another regression? What is the chance that I have beta 1 hat, which is as extreme or even more extreme than my current one? Okay? And we don't want to forget that you have to multiply 2. Why? Because it's two-sided test. Okay? Now, do we have to remember anything for this p-value? The answer is no. I produce p-value along with the standard error and t-value too. Okay? So you can simply use R output to get the p-value, but it's better to remember that that's the meaning of the p-value, and this is how I calculate everything. Now, the last step is to make a decision. If p-value is too small, reject them. Okay, so this is our p-value method. So essentially you have two methods. You either use t-value, too big or too small, the p-value method. P-value is very small, it means that the null is very unlikely. Now, do you have any questions so far? Is everything okay? Now the next topic is confidence interval. So let me review one thing. Suppose that a random variable follows the standard normal distribution. That's the how it looked like. Do you remember this notation? G of 0.05. What does it mean? By the way, the center is 0. So in statistics, this value means what is the value of the random variable such that the probability to the right is equal to 0.05, 5%. Now the probability to the right from the center is 50%. So it's going to be quite far from the center, right? So what is the value of this random variable, this point, such that the probability, the area, is equal to 0.05? Do you remember this value? It's 1.64. So likewise, what does it mean? What is the value of the random variable such that the probability to the right is equal to 0.05? 0.25, 2.5%. So that's 1.97. So it's essentially the value on the x line, the horizontal axis. So this is 1.64 and it's symmetric. So suppose that this is minus 1.64. What does it mean? The probability to the left is again 0.05, right? So sometimes we write something like this. So the probability to the tail is the probability of having an extreme outcome, right? The probability in the middle is the opposite. So can you imagine that we assign most of the probability in the middle, like 1 minus alpha in the middle? What is left is alpha, and we have left-hand side and right-hand side. So we like to give half of them. Okay? So in the middle, you have 1 minus alpha probability. On the left-hand side, you have half of the alpha probability. And g of alpha divided by 2 is the value of the random variable such that the probability to the tail is equal to half of the alpha. So the example is, g is 0.1, g of half of the alpha is g of 0.05, that's 1.64. If alpha is 0.05, g of half of the alpha is g of 0.025, that's 1.97. Okay? Now we can define the confidence interval. Now let me give you two examples. Now let's think about when the alpha is 10%, then 1 minus alpha is 90%. So we are talking about the 90% confidence interval for beta 1. What is it? Beta 1 hat plus minus. What is this g value? And alpha is 0.1. It's 1.64 times standard error. Okay, so that's the 90% confidence interval. What about 95%? So 1 minus alpha is 95%, 0.95. Alpha is 5%, 0.05. The g value is 1.97. So we can go further. What about 99% confidence interval for beta 1? That's beta 1 hat plus minus. Do you remember the value of g such that the middle is 99% and the right-hand side is half of 1%? Is it 2.3 or 2.5? Yes, it's 2.5 something, right? $2.57. So you can go on and on and on. Now center remains the same. It's your regression coefficient from your sample. What happens if you increase the this level? So it's the same center, plus minus. It's about 1.6 times standard error. It's about 2 times standard error. It's about 2.6 times standard error. So you need an interval which is wider. Okay? So in words, if you want to be more confident about your interval, you have to make it wider. Does it make sense? Okay, so let's do this. So I think by this, you can solve everything in the homework, okay? So why don't you try it first? So try your homework. And if you have to, you submit it by Tuesday, next Tuesday. And then we'll think about the meaning of what you did. Like if you calculate the standard, the confidence interval, we'll think about what's the meaning of the interval a little later. Okay? Okay. So perhaps I stop here today. So once you come back, I finish a few things that is left in this reading guide, and we are going to move on to the next topic.